You ever wonder how that tiny mirror on the side of your car can show you an entire truck? Or how a massive telescope can pull in light from galaxies light years away? Well, it all comes down to the amazing physics of curved mirrors. And today, we're going to break down exactly how they work their magic.
So here's our game plan. We're going to start with the one fundamental law that rules them all. Then, we'll get to know the parts of a curved mirror. After that, we'll dive into the 4 simple rules light always follows, see how those rules create the images we see, and finally, we'll wrap it all up with the neat bit of math that ties everything together.
All right, let's get right into it. Before we can even talk about curved mirrors, we have to understand the one single law that governs any kind of reflection. Doesn't matter if the surface is flat, curved, or bumpy. It all boils down to this one simple, beautiful rule. As you can see right here, the angle of the incoming light ray, that's the angle of incidence, is always exactly equal to the angle of the outgoing ray, the angle of reflection. Now, we measure both of those angles from this dotted line called the normal, which is just a line drawn at a perfect 90-degree angle to the surface. And that's it, seriously. This one law is the key to everything that follows. Okay, so we've got the law down, now let's look at the mirrors themselves. To really get how they work, you gotta know their anatomy. So, let's meet the key players.
So, there are really 2 main characters in this story. On the right, you've got a concave mirror, which, caves in. It's built to gather light and bring it together. And on the left is the convex mirror, which bulges out. Its job is to spread light out. You can think of both of them as just slices cut from a bigger hollow sphere.
First up, we have the pole, which we label with a P. Just think of the pole as the absolute center of the mirror's surface. It's our main reference point, our ground zero for all the measurements we're going to make. Next is the center of curvature, or C. This is literally the center of that big sphere the mirror was sliced from. How far C is from the mirror tells you everything about how sharp that curve is.
And now for the most important part of all, the principal focus, or F. This is where the real magic happens. For a concave mirror, it's the exact spot where parallel rays of light all meet up after they bounce off. For a convex mirror, it's the point behind the mirror where those scattered rays look like they came from.
Okay, here's the best part. Light might seem wild and chaotic, but when it hits these mirrors, it follows 4 incredibly simple and predictable rules. Once you know these 4 rules, you can trace the path of any light ray and figure out exactly what kind of image you're going to get.
Rule number 1 is the big one. Any ray of light that comes in parallel to that main center line, the principal axis, is going to reflect and pass right through the focus, F. Now look over at the convex mirror. For that one, the ray bounces off as if it came from the focus point that's behind the mirror.
And rule number 2, it's just the perfect reverse of rule 1. If a light ray passes through the focus before it hits the mirror, it's going to bounce off perfectly parallel to the axis. See? These first 2 rules are like a perfect logical pair.
Now, rule 3 is the easiest one to remember. Any ray that passes through the center of curvature, C, hits the mirror dead on, at a perfect 90-degree angle to the surface. And because of that, it just reflects straight back along the exact same path it came from. No change in direction at all.
And our final rule brings us right back to where we started. If a ray hits the pole, the very center of the mirror, it will reflect perfectly symmetrically. In this one special case, the principal axis itself acts as the normal line. So just like our first law said, the angle in equals the angle out. Simple as that.
So we have the rules, let's put them to work. This is where it gets really cool. By drawing just 2 of these 4 rays from an object, we can find exactly where they cross. And that intersection point tells us precisely where the image will form, how big it'll be, and whether it's right side up or upside down.
This table here is basically a cheat sheet for concave mirrors. It shows you what happens as you move an object closer and closer to the mirror. Look at the pattern. Far away, the image is small, upside down, and real. As you get closer, the image gets bigger and bigger until you cross the focus point, and suddenly it flips to become huge, right side up, and virtual, appearing behind the mirror.
And here's what that looks like in a diagram. This is that first case from our table. See? We draw one ray parallel to the axis, that's rule 1, and another one through the focus, that's rule 2. And look where they cross, that's our image. And just like the table predicted, it's smaller, it's inverted, and it's located between C and F. It works every time.
Now, convex mirrors, they are way simpler. Honestly, they only tell one story. It doesn't matter where you put the object in front of a convex mirror, the image is always going to be behind the mirror, it's always going to be smaller, and it's always going to be virtual and upright. This super predictable, wide field of view is exactly why they're perfect for things like car side mirrors and security mirrors.
Drawing diagrams is fantastic for getting the concept, but what if we need to know the exact location and size? For that, we turn to the math. There's a surprisingly simple code behind all this geometry.
While drawing rays is great, for real precision, we have this beautiful piece of math, the mirror formula. It's an elegant equation that perfectly connects the three most important things: the mirror's focal length, f, the distance of the object from the mirror, u, and the distance of the image, v. With this, we can calculate everything without drawing a single line.
Okay, but there's one catch. To make this formula work, we all have to agree on a set of rules for our numbers, what's positive and what's negative. We use something called the Cartesian sign convention. It's actually pretty easy. Just imagine the pole, P, is the 0 on a number line. Light always comes from the left. So, any distance you measure to the left of the pole is negative. Any distance to the right is positive.
So let's break that down with a quick cheat sheet. Since the object is always on the left, its distance, u, is always negative. For a concave mirror, the focus is also on the left, so its focal length, f, is negative. But for a convex mirror, the focus is behind it, on the right, so f is positive. The exact same logic applies to the image distance, v. You just stick to these rules, and the formula gives you the right answer every single time. And one last thing, what about the image size? Well, that's called magnification, or m, and it's just a simple ratio, negative v divided by u. The number tells you if it's bigger or smaller than the object, and get this, the sign tells you its nature. If m is negative, the image is real and inverted. If m is positive, it's virtual and erect. So useful.
And this flowchart here basically brings everything we've just talked about together in one place. You can see the two types of mirrors, the formulas that describe them, the ray diagrams we use to visualize them, and their practical, real-world uses. It's a great snapshot of how all these ideas connect to each other.
So we've just seen how a handful of simple, elegant rules can perfectly predict the seemingly complex behavior of light. And that brings me to a final question for you to think about. What other forces in our universe, maybe from the orbits of planets to the interactions of tiny particles, might also be governed by an underlying set of beautiful and predictable laws, just waiting for us to discover them?